Hello, everybody. Bonjour, Madame Monsieur. That's a little French, I know. This talk gonna be about concurrent garbage collector implemented in the Kotlin native runtime. I'm Nikolay. I'm working on Kotlin native team and implemented this this collector, so have some first-hand knowledge of that. Okay. So, quick recap on Kotlin native. How many people here in the room actually use Kotlin native? Oh, amazing! That's very nice. You probably know that, and for everybody else, just let me mention that Kotlin native is a compiler which takes Kotlin source code files, Kotlin binary libraries, native binary libraries, static, dynamic, or Apple frameworks, and can produce the native binary which can run on a computer without need of virtual machine runtime or other execution context, just as a regular executable, and it's relatively small size, so like several hundred K is your typical Hello World application. It very important part of the Kotlin native is actually interoperability. So, as every Kotlin program has Kotlin object, Kotlin functions, but it's not enough. So we need to be able to interoperate with Swift objects and with Swift function, and do that in a very multiple way, I'd say. So, for example, Kotlin object shall be able to extend Swift classes, encapsulate references to Swift classes, and the opposite. Swift object must be able to refer to the Kotlin object. The same holds for Kotlin to Swift functions. So Swift functions or blocks, how they call it in Objective-C language, could be stored as a field in Kotlin objects. Also, Swift must be able to refer to a Kotlin function, because both languages are functional in a sense that functions are first-class citizens. So all possible combinations. Same holds with C. Although C is not object-oriented language, it still has structs which essentially predefined memory layout, and it has notion of functions. So we must be able to refer to C structs, instantiate C structs, use fields in C structs. Do the same with C functions, so invoke C functions, refer to C function as a function reference in Kotlin terminology. Do that in opposite direction, and invoke C function from Kotlin and Kotlin functions from C. So so this interoperability story in Kotlin is very rich, and we actually have to support multiple scenarios. So, to implement all that, we need to have support for automated memory management, because Kotlin is a high-level language. It has automated memory management, and automated memory management is typically one of the most complex part of any runtime. And as I mentioned, automated memory management in Kotlin native made even more complex, because you need to interpret. You see, it's if you want to create an object in Kotlin, it's okay. But if you really want to be sure that this object could be passed in some form to C or Swift world, and then it's up to Swift runtime or C code to actually interact with it, you need to be very careful in managing your memory. So we implemented memory management in Kotlin using reference counting. It's a very popular technique for memory management implementation in native languages. So, for example, it's implemented the same way in Swift, and in many C++ libraries. It also uses reference counters. So let's take a look at how it's implemented for a very simple Kotlin code snippet I have here. So we have a data class which has two fields. One is a string reference, another is a primitive of int type. And what we do in a function, we just instantiate such a class and print out one of the fields. So how it looks, the situation looks for the runtime. For the runtime, we have execution stack, which keeps object slots. So references to objects are stored on a stack, and so when we create an instance of data, we have a slot which referring to an instance of data, and it has reference counter of 1 because there is only one reference to that from the stack, and inside it has a field name which refers to instance of Kotlin string object which has information we typically have in string, such as length and characters. And the reference counter of that object is 2 because we refer to that from both data and from anonymous slot used for retrieving this field from instance and store it on a stack so that we can pass it to println function. So as you see with reference counting, whenever we refer to like this reference accounts in this number. So this 2 is actually exactly the number of incoming edges, incoming references. And once we no longer need this object, so for example, when we leave the function, following happens. There are no references referring those objects from the stack. So this reference count decrements to 0. This decrements to 0, and as this object gets destroyed, it also decrements to 0. Whatever it refers to. So those two objects go away. So that's how any reference counting system works, not only Kotlin native. So the cyclic references. The well-known problem with reference counting systems is the presence of cyclic structures, where which one we can see in this particular simple example. So we have a linked list which has two fields, data and a pointer to the previous element. And so when we instantiate like the first element, we instantiate the second element, and then we make this a cycle by assigning the previous element to x2. So as a result, we end up in the following layout for the runtime. On a stack, we have two slots. One points to x1, another points to x2, and let's look at the reference counters. So the reference counter here is 2 because you see it's being referred by stack and it's being referred by x2. The same as here. We referred from stack and we referred from x1. So imagine that we leave such a frame. Then all those two references go away, but the reference counter is still non-zero. It's 1 in here and here. just because we still not able to reclaim this unreachable object. So that's a typical, once again, typical problem with cyclic references in any reference counting system. That's not unique for Kotlin. And some languages like Swift pretty much ignore that as a problem. They consider it responsibility of the programmer to actually not create the cyclic references. But in case of Kotlin, it's unlikely looks like a good idea, because we have Kotlin multi-platform, and a lot of code written for JVM, which is a pure Kotlin, better be reused in Kotlin native. So we decided to provide better runtime guarantees and provide ability to collect a garbage like that. So how we did that? We did that by implementing an algorithm called trial deletion. So let me describe in details. Imagine we have object graph. Here the actual types of objects are not important, but what's important is the reference counter. So here this 1 and 2 is actually the number of incoming references. So, and this is and this reference is, for example, reference from the stack. Okay, so so imagine that this reference from the stack goes away. So what we do in a trial deletion, we remember elements which whose reference counter goes to non-zero values in a special set. It's marked in brown in here, and we periodically run certain analysis. The analysis which I will describe, it's called trial deletion. So how this analysis works? What we do, we go starting from this to release set, and traverse by inner references and decrement references of whoever we point to. So here this object was referring that object, and its reference counter became 0 because we just traversed this element. Then we repeat this operation and now traverse here, so that we decrement reference counter here to 1. Then we repeat this operation, and by traversing link here, we decrement this to 0. And finally, we traverse from here to here, and we end up in all edges equal to 0. And so we can mark those elements as no longer important for the programmer because they're garbage, and so we can dispose them. So just to show you the viability of algorithm, consider a little bit different situation where we once again have the same object graph, but this node has external reference. So we traverse it according to the same algorithm, starting from a freshly released one. Once again we iterate over the nodes, but then we reach a situation when we traverse the whole graph, but this node, it doesn't have 0 reference count. It has one reference count of 1. So we backpropagate starting from all such objects. We backpropagate and increase reference counter traversing by inner references. And so we end up in pretty much original reference counter, and this was valid non-garbage, and we detected as such in this trial deletion algorithm run. So this was all good, and actually was functioning pretty well for single-threaded execution scenarios. Because we can run this trial deletion by essentially preempting execution of the current thread. We can do these liberal modifications of reference counters. We can traverse the inner references and be sure that nobody changed them. So it's all good and fine. However, it's not going to work in a concurrent scenario. And in concurrent scenario, there are two possible kinds of objects. Some objects could be shared, so they they actually seen by more than one thread, and the reference counter, for example, must be updated using atomic operations, and some other objects are local, so their reference counter could be updated by just regular arithmetical operation, and as they're not visible to all other threads, it's not important. So those two classes of object are inherently different. So we introduced a notion of object freezing to actually allow sharing of immutable data in the memory manager mechanism I described earlier. So how we did that? Consider this this structure. It has a cycle, and it also referred from some other external object. We perform an algorithmical operation called graph condensation. So this is a theorem from computer science that essentially arbitrary graph could be split into so-called strongly connected components, and the graph of those strongly connected components by itself will be directed as cyclic graph. This theorem means that if we apply the following transformation, if we're able to identify this strongly connected component is a pretty simple concept. It's a set of all objects where each object is reachable by going the reference. Oops, that's unexpected. Okay. So strongly connected component is exactly those three objects, because if you go from that object, you can go here, you can go here, you can go here, and so it has interesting property that it's reachable from every component. So what we do, we perform so-called condensation. Condensation is essentially grouping all those objects, because they guaranteed to have coinciding lifetime as they're referring each other, so they cannot have a different lifetime actually. So we consider them to be a single object with total reference of count of 2. So if you sum the reference counters of all objects on the left hand side, you'll see it's 5. That's why it is 5 here. But if you discount inner references, so this object refers this one refers this, and this one refers this, then it ends up being 2. And 2 is the reference counter we assign to this condensed component, and it's exactly the number of external reference, so from here and from here to this whole condensed component. And we other than aggregating the reference counter for strongly connected component, we also mark this object as immutable. So those two operations together, it's called freezing in Kotlin native, and that's pretty frequent operation used once you want to be sure that certain object could be shared across multiple threads. So that's all good, and actually let me go back a little bit. So in this scenario, actually we have interesting property that once we perform this condensation, we can actually release this aggregate object without analyzing its internal structure. So we don't have to analyze it for cycles using algorithm like trial deletion, because it cannot participate in any further cycles, because it's immutable, so the reference here can be changed, and by the way we build it, it's exactly the strongly connected component. So it's a cyclical structure. So we can just once we just decrement reference counter several times, and when we reach 0, it means this whole aggregate is no longer needed, and we can throw it away. So it's easy. Now we can share object, and we can avoid memory leaks, but at the same time keep keep objects in shared state. Now, the fancy part. It's all good and correct. However, it's not powerful enough. Especially for people coming from JVM, this model was looking pretty much restrictive. And it was very popular request to have, okay, my objects are all immutable, but at least can I have a mutable pointer, so that if I share a pointer, I can, before I had some data pointed by the reference, and now I have some other data, also immutable, pointed by these references. So we introduced the notion of atomic reference. Atomic reference is just a simple box class which contains a pointer to some other class. But the value stored in atomic references can change, so we can assign to the value. So it's kind of exception from immutability rule of shared objects in Kotlin native world. So let's look at this example, how it's represented in a runtime. You see, we have, once again, we have a cyclic structure, because atomic reference refers to F2, F2 refers to F1, and F1 refers to A1. And we cannot collect this cycle. That's a real problem, because it means it's a memory leak, and child deletion will not work on that, because all those objects are published, and child deletion can only work on the local objects where we can avoid modifications in object graph and reference counter by someone else. So we have memory leak. This was the situation with Kotlin native runtime until 1.4 release. So in 1.370, for example, you can create this way. You can create a memory leak, and some people actually do. One especially nasty customer was kotlinx.coroutines once it tried to implement multithreaded mode. So, welcome the cyclic collector. Idea was to provide a mechanism to collect the garbage created from such situations related to atomic references, but at the same time not interfere with the regular operation of the runtime. So that, for example, if you have UI thread, you still don't want UI thread to be interrupted by this collector. Everybody knows how bad it could be if your UI program freezes in the middle just because garbage collector decided it's time to run. So one of the primary design of this cyclic collector was that it's executed in the background. We have dedicated GC thread, and whenever threads are working, they manipulate on some shared data. But garbage collectors only care about the subset of the shared data, and namely it's a set of all atomic references present in the program. We call this set of atomic references atomic root set. So GC thread maintains internal knowledge about the atomic root set. And how it operates then? We have GC thread running, and you see this is exactly the data structure we have earlier. So we have A1 referring F2, F2 referring F1, F1 referring A1. And in a GC thread, we perform the following algorithmic trick. We assign to each element of the transitive closure reachable from A1. The transitive closure is essentially a set of all elements reachable if you go by reference. So, for example, the transitive closure of A1 is exactly A1, F2, and F1. So when we analyze the object graph in our concurrent collector, we assign every element of this transitive closure the site reference counter. Site reference counter is it could also be called inner reference counter, and it's computed pretty simply. You start from A1. That's an element of atomic root set, so you know about it. You follow this reference. You increment the atomic site reference counter associated with F2 and make it 1 now. Then you follow this reference. You increment a reference counter associated with F1, and now it became 1. And then you follow this reference and increment the atomic site reference counter associated with A1 and make it 1 again. And now notice an interesting property of this site reference counter. If there are external references, so for example, if there would be an additional edge pointing to F2, then it wouldn't match. It would be like 2 versus 1. But if they coincide, then we have an interesting property. We can ensure that all references are actually inner. So they're not coming from anywhere, but from references inherent to atomic root set. So it essentially belongs to like transitive closure of A1, and at the same time they're not reachable from outside world. So that's what they call garbage. And so what we can do once we realize that it's actually a garbage, we can of course collect it. But as I said, this garbage collector is very non-intrusive, so it goes even fancier. It just zeroes out this reference, and so break this cycle. And once it zeroes out these references, then all those references are collected automatically by the regular memory management algorithms. So that's like the good story. Now let's think about the bad story. Imagine that during this traversal, GC thread was looking at this object graph, counting those side reference counters, but as I mentioned, atomic reference counter pointers, unlike other pointers, you see it. This edge, for example, can never change because it's frozen, but this edge actually can change. So what we're going to do in such a situation? If it was updated, then it points to some F3, and what happens is we end up in a situation where our analysis is just incorrect, because we partially analyzed one graph, but graph has changed under our hands, and so it's like we compute some meaningless number if we complete this algorithms. So what we're gonna do? As we know all elements of atomic root set, we know also about updates in the values of atomic root set. So we can just stop GC analysis and restart it from the very beginning whenever the value stored in atomic reference changes. So it means once we can be sure that the graph changed under our hands, we have to restart analysis. This is an interesting part because it means that essentially our stealth GC, actually that's why it's stealth actually, because it tries to operate in a background and only run in the relevant moments. It just have to restart whatever it did, but fortunately it doesn't affect the operations of the program, not at all. So you just we just continue updating our pointers in normal threads like nothing changed. It's just a GC thread which itself have to restart its computation for the side reference counter. And also to prevent GC trashing for situation when atomic references are updated very frequently, and we cannot collect the garbage. We implemented automated throttling. So if we've seen a lot of GC interruption operation, then we just sleep gets a thread for some time and let mutation phase to proceed and just resume a little bit later. So this means that once again we're receiving pretty interesting properties of the collector, which are not very typical for your regular collector. It's not distracting for the program. So usually most concurrent collectors they have expectations that collector runs in such a mode that it's pretty intrusive to the program workflow, and here it's absolutely not distracting. It just pretty much executes in the background. Also, it runs when it can. So, like when transitive closure of atomic root set stabilizes, GC sees that moment and find the garbage. When it's heavily mutating, okay, I wait a little bit and just do nothing. And curiously enough, it only runs in relevant scenarios. So if program is heavily concurrent, then yes, it will run. But if there are no atomic references in program, then the GC thread just sits in the background and does nothing, because it's essentially activated by conditions related to updates of atomic root set. So that's pretty much the talk I wanted to give, and this is all very new development. So this code was committed to Kotlin native master about 2-3 weeks ago. So now it's functional. It's known to pass like most stress tests, including stress tests from some kotlinx.coroutines, for example, and we internally did a lot of reviews and algorithmical analysis. But you are more than welcome to ask questions, have suggestions, or maybe even prove that the algorithm I have described is is incorrect or need to have improvements. So, your questions?
So, as I understand it, the garbage collection thread is only useful if and only if there are atomic references.
Mm-hmm.
So, every other scenario is handled synchronously by each thread, by the runtime in each running thread, right?
Yes, absolutely.
Okay, so what's the... that means that there must be stop the world events for you to... every time a reference count is brought down and reaches not even 0. Every time a reference goes down, then you need to perform this cyclic reference detection.
Not at all. It's no. Thank you for the question. Yes, it's probably not in the scope of this question, because it's a general how we activate the trial deletion, I guess. And the answer is we activate the trial deletion once we have sufficiently big release candidate set size. So we not do that on every like element appearing in release set, but instead we accumulate like several thousand elements, and the actual value is adaptive depending on the workload of the application and time of and frequency of local GCs. But we essentially try to adjust this buffer size to better reflect the workload. But other than that, we amortize the cost of trial deletion generally.
Okay. And my other question was, okay, Is the garbage collection thread started every time, even if you don't know yet if there will be atomic references, or do you wait for the first atomic reference to pop out to create and launch this garbage collection thread?
In current implementation, we started on essentially on the start of the first Kotlin native runtime. So yes, we started unconditionally. Although you're right, in theory we could do that on the first atomic reference creation. It could be a good optimization.
Thanks.
Thank you for questions.
Great talk.
Hi, you mentioned there are limitations to the way it works with the current version of Kotlin native 1.3.7 regarding the atomic reference counting. Are there other limitations with a garbage collection with Kotlin 1.3 that are going to be fixed in 1.4?
Okay, thank you for the question. I think the main limitation which was lifted by this work was that before atomic references could be the source of memory leaks. So semantically there was no limitation, but it could lead to memory leak if not carefully released. And so after this work, the memory leaks are handled automatically by the garbage collector, which is one of the very typical cases where people could create unintended memory leaks. Was actually lazy delegate, because if you have frozen object with lazy delegates, then it's implemented using atomic reference actually internally. So so in theory you could create a cycle this way, for example.
Okay, and are you aware of other Kotlin libraries that use atomic references internally, such as maybe coroutines or something else?
I think kotlinx.coroutines is a very heavy user of atomic references. Moreover, they actually use a slight modification of atomic references called freezable atomic references, which are mutable, depend a little bit different depending on if they're frozen or not. But yes, actually, one of the main motivations of this work was concurrent kotlinx.coroutines support. At some moment Roma came to me and said, okay, I found 10 memory leaks, but there are some unknown more, and I have no idea how to debug them. I first started with the creation of the tool which allows you to find the memory leaks automatically, but then we realized that some of those memory leaks cannot be actually fixed by without very serious rework of kotlinx.coroutines code base. So we realized that it's probably easier to implement a collector like that, which is beneficial anyway.
All right, thank you.
Thank you.
Hello, thank you for the talk. You just mentioned you had some tools to debug memory leaks. Is that something we can use too, or is that some internal tools?
No, it was APIs which we implemented in Kotlin, but actually after after I added this cyclic collector, I removed those tools as they are no longer relevant. It's only about sharing, finding shared cycles. It's not about general purpose memory leak analysis tool for things like C allocations or Objective-C. It was purely Kotlin native cycles like that one.
So now that it's fixed, it's not used anymore. This is
yes, it's not used anymore, and actually I removed this API. It was experimental, so
cool.
It's no longer there.
Yes, thank you very much for your talk. It was really clear. Where did you find inspiration for this implementation? Like for the traditional retained cycle is it's, as you said, it's more or less widely used in this domain. But for this concurrent thread implementation, Do you have sources that inspired you, or it was like a personal research?
Okay, actually, I can tell you where I came to this idea, but not from which from which regions. I think I was laying on the beach in Thailand, and that was the place of inspiration. that's I'm pretty good. Remember, I just realized that if you think about this algorithm, it's actually pretty similar to trial deletion, and actually that's why in a first part of the talk I cover the trial deletion. So in a sense, inspiration is to apply ideas of trial deletion, but instead of doing this in place, inside of an object, do that by side. And so once you reach certain graph property, once something became a garbage, this invariant holds no matter if it's computed inside of an object or in a side structure. And considering that transitive closure originating from atomic references is relatively small, it's possible to maintain the side structure and not inline it into the objects. So.
And second question: how do you test this against regressions? How do you unit test this?
Well, I essentially use kotlinx.coroutines test. I wrote some of my own tests. I have very intensive code review. So if you take a look at Kotlin native repository and dig out this code review, I have amazing colleagues. He has a lot of how do I say, mind experiments, which he backed up by certain by code patterns showing deficiencies in various forms of algorithms. So we were thinking a lot about how this algorithm gonna work, and we did some testing. So that's combination essentially.
Thank you.
Thank you for the question.
Thank you.
Thank you. Thank you.